This will be a brief refresher on differential operators. Let's start by recalling partial differentiation of a function. Consider the function v, which is scalar, meaning that it only has a value, and depends on three Cartesian coordinates, x, y and z. Then we can define partial derivatives of that function in respect to any of the three coordinates. When evaluating a partial derivative in respect to one variable, we always assume that all other variables are constant. This scalar function may represent in reality an electrostatic potential voltage in some device. We can work out the electric field and the force on a charge that is moving through this device. Then we introduce the mathematical operator del, designated by the inverted Greek letter delta. Operator must act on a function. When del operator acts on a function, it takes partial derivatives of that function in respect to every Cartesian coordinate and makes them into corresponding Cartesian components of a vector. Remember that del is an operator. It has no meaning without a function on which it must operate. It takes a function in three-dimensional space and assigns a vector to each point in space where that function has all three partial derivatives. When del operator acts on a scalar function, it is called a gradient. Consider, for example, the following scalar function. By taking the corresponding partial derivatives, we obtain the gradient of that function shown here. The gradient is a vector. Formally, it looks like a product of the vector del and the scalar v. From first-year physics, you should remember that in one-dimensional case the electric field is given by derivative of electrostatic potential or voltage in respect to coordinate r. In the three-dimensional space, electric field vector is given by the negative gradient of electrostatic scalar potential v. You can also apply the del operator to a vector function. A vector function itself has three components. With del being a vector operator, there are two ways you can apply it to a vector function. The first way is similar to scalar or dot product of two vectors. Applied in this way, the del operator is called divergence. You simply add the three partial derivatives taken from the corresponding components of a vector function. Thus, the divergence is a scalar. It takes a vector function in three-dimensional space and turns it into a scalar function. You can also apply the del operator to a vector function in a way similar to the cross product of two vectors. Applied in such a way, the del operator is called the curl. The curl operator is a very important one, as it relates the changing electric field to the magnetic field in an electromagnetic wave, for example. In Cartesian coordinates, the curl is given by the same determinant as the cross product, except that in the second row we have partial derivatives instead of values. Obviously, the result of such an operation is a vector with Cartesian components given by the difference of the remaining two partial derivatives taken of the other component of the vector function. If curl of a vector function is zero everywhere, such a function is called curl-less. For example, if we use the function e from previous examples and perform the curl on it, we get the answer as 0. Try it yourself. Another important operator which you will often encounter in this course is the Laplacian operator, or simply the Laplacian. It is formally obtained by the dot product of two del operators. It is the second-order differential operator, meaning that it involves second partial derivatives. It is simply given by the sum of the second partial derivatives in respect to the three Cartesian coordinates, x, y and z. The Laplacian results when you apply del operator consecutively, first as the gradient and then as the divergence. Thus the Laplacian is the divergence of a gradient. Laplacian can act on both scalar and vector functions. When it is applied to a scalar function, its result is also a scalar. Applying it to a vector means that it is applied to each component of that vector separately, therefore the result is also a vector. It is important to understand that del operator is defined and has the simplest form in Cartesian coordinates. In cylindrical or spherical coordinates it will have a different and more complicated form. Nevertheless, it is often useful to work in those coordinates, because some additional complexity of the del and the Laplacian operators are more than compensated by the simplicity one gains from the symmetry. Here is just an example of applications of the del and Laplacian operators to scalar and vector functions in cylindrical coordinates. Note that they are expressed in terms of partial derivatives in respect to cylindrical variables r, p and z and the unit coordinate vectors corresponding to those coordinates. The unit vector corresponding to each cylindrical coordinate point in the direction of infinitesimal increment of that coordinate. Those directions are different at different points in space. For instance, a sub p points tangentially to the circle going around the axis z through the point and it rotates as you go around the circle. These are just some useful vector identities involving scalars, vectors, the dot and cross products and the del operators. You should be able to derive most of them, but there is no need to memorize them. You can always look them up when needed.